octet rule in molecules except for, and if we check out the answer to this one here would be nitrogen. Remember that when we look at elements that exceed the octet rule, we are looking at which elements? Where do they lie? Jed?
Groups 15, 16, 17.
Yes, groups 15, 16, and 17. And where do they start?
Second, period 2.
Right, period 2. Not period 2, period 3. Yeah, period 3. Except for argon, which we go down here. So basically all of these elements below here are going to exceed the octet rule. Nitrogen's not a part of that, so nitrogen would not exceed the octet rule. Any questions on the first one? Okay, then if we look at the next question on the Socrative app here for today, was which one of these species is a free radical, that is, has an odd number of electrons? Well, if you start adding all of these up and summing together valence electrons, you're going to see that all of them have an even number except for NO2. And that's because if you sum together valence electrons, nitrogen has 5. Each oxygen has 6, so we wind up with a total of 17 valence electrons in this one. All the rest of these here have an even number if you sum them together, so nitrogen dioxide would be the one that is the free radical. Any questions on either of these two? All right, let's pull your handouts out, and what we're going to do today is we are going to be looking at what's called formal charges. And let's see where we have formal charges discussed here. Formal charge, we say, is a hypothetical charge. And when we say it's hypothetical, that means it's not real. It doesn't dictate. There is not parts of molecules that are positive or negative or anything. So there's going to be no attractions that occur between things that we assign positive charges, no repulsions, or no attractions when they have opposite charges, no repulsions when they have like charges, but rather it's something we do to help tell us which structure is the best one. So we have a formula for calculating it here, and what that formula comes from is we say that all of the bonding electrons are shared equally between the bonded atoms, and all of the lone pairs of electrons belong entirely to one atom. And one of the ways we do this, and one of the reasons for it, is that sometimes we can't explain why things bond the way they do. For example, the other day we were writing out structures for the sulfate ion, and I don't remember where exactly we did this one. But right here, we came up with a structure for a sulfate ion that looks something like this. And it turns out that this is not actually what we find to be the actual structure of the sulfate ion. And formal charge actually helps dictate to us what is the best structure. So we're going to start this particular one as a basis for looking at formal charge. We'll go ahead and regenerate this one. And we'll start then by looking at sulfate and do it the way that we traditionally have written out its Lewis diagram. That is, we sum together the valence electrons, and we have sulfur, which has 6 valence electrons, each oxygen that has 6. We have 4 oxygen atoms, and then of course a 2 negative charge means we have 2 extra electrons. When we sum these all together, we wind up with a total of 32 valence electrons. So then what we did when we generated this the other day, we put the sulfur atom in the center, we surrounded it with the 4 oxygen atoms, like this, and then what we did is we said that this used up 8 valence electrons, meaning we have 24 left to go. And then we put in the remaining valence electrons as pairs to the surrounding atoms. And that would be 10, 12, 14, 16, 18, 20, 22, 24. And so again, we'd kind of left it like this. But now what we're going to do is we're going to take the structure and we'll do this. We're going to say that we are going to write a Lewis structure that optimizes the formal charge on each atom. So we're going to write a Lewis structure that optimizes the formal charge on each atom. Now, to optimize the formal charge, we have some rules here that help dictate to us what optimizes those formal charges. One of them says here that when we try to select the best Lewis formula, small values, especially zero values for formal charges on individual atoms, are better than larger ones. And secondly, it says when formal charge cannot be avoided, the most electronegative atom should be assigned a negative formal charge. So what we're going to do with this one here is we're going to go ahead and calculate what the formal charge is as it exists on this polyatomic ion right now. And so have your formulas handy here, the formula for calculating formal charge. And it says what we're going to do is we're going to take the valence electrons that are on the free atom. So let's go ahead and look at something like the sulfur atom here in the center. And we're going to calculate the formal charge on the sulfur. And the sulfur now, as we have it written, is showing 4 bonds. So to calculate its formal charge, we take the valence electrons in a free sulfur atom. And how many valence electrons does a free sulfur atom have?
6.
6, okay. So we're going to start with that number right here, 6. And then we're going to subtract from it, according to the equation, the lone pair electrons. So any electron that's in a lone pair on the sulfur, we subtract those. So how many lone pair electrons are there here? None. So we'll subtract 0. And then the next thing we're going to do is we are going to subtract from it 1/2 of the bonding electrons. And we subtract 1/2 of the bonding electrons because what it says here is that we assume that when we calculate it, that the bonding electrons are shared equally between the bonded atoms. So what that means then is that if we're looking at this bond right here, it's saying that 1 electron belongs to the sulfur, 1 to the oxygen. 1 to the sulfur, 1 to the oxygen. 1 to the sulfur, 1 to the oxygen. 1 to the sulfur, 1 to the oxygen. So when we're saying we're going to take 1/2 of the bonding electrons, we're really only showing the ones that come from the sulfur right now, which is 4. So 1/2 the bonding electrons, there's a total of 8 bonding electrons, but again, half of those is 4. So we are going to subtract 4 from there. And once we subtract or calculate this out, what do we get when we take 6 minus 0 minus 4? All right, and we're going to show that the +2. Now, because this is not an actual charge on a particle, we show the sign in front of the number. Remember the convention is we show the sign on the back end when it represents an actual charge on a particle, but this is a hypothetical charge, so it's not a real charge. We say its formal charge is +2. Then if we go ahead and calculate the formal charge of an oxygen atom, right here, we can do that. So for oxygen, this oxygen here is forming 1 bond. And with 1 bond, we then follow the formula, which says we take the number of valence electrons in a free atom. So a free atom of oxygen has how many valence electrons?
6.
And then we're going to subtract from this the number of lone pair electrons. So the number of lone pair electrons in this case is 6. And then we take 1/2 of the bonding electrons. So 1/2 of 2 is 1. So we take 6 minus 6 minus 1, which is going to give us -1. So now, if we went through and looked at the structure, we could write in these formal charges. Formal charge here on the sulfur is a +2. Oxygen here, -1. Oxygen here is a -1. This oxygen here is a -1. This oxygen here is a -1. So what I've done here now is I've just gone through and written in all of the formal charges. If we've done our job properly, oh, and by the way, why did I not have to calculate it for all of these other oxygen atoms?
They're all the same.
Yeah, they're all the same. They all have one bond. So they're all done the same way. So now if we sum together all these formal charges, what is the sum of all these formal charges that's in here? Right. And of course it should equal the sum of, or it should equal whatever the charge is on the particle. If it's a neutral molecule, it should sum to be 0. If it's a polyatomic ion, it should sum to equal the charge here on the ion itself. So this then is the way that we'd write this out. Now what's not good about this is this. First of all, we don't have any of them that have formal charges of 0. And so ideally then, when we try to minimize formal charges or optimize formal charges, we like to have as many 0 values as is possible. In this case here, we don't have any that have 0 values. Secondly, it says when formal charge cannot be avoided, the most negative, electronegative atom should have the negative formal charge. So if at the end we have a formal charge, and we're looking at this sulfate ion, the negative formal charges should belong to which element between the sulfur and the oxygen? This should be obvious. It should belong to the oxygen because the oxygen is the one that has the larger electronegativity. So at least what we do have right now, that's good because the negative formal charges here are the more electronegative, but again, they are too far away from 0. We like to get as many as close to 0 as possible when we can. So one of the things we should remember here now is that sulfur is one of the atoms that can exceed the octet rule. Okay, remember that there are some exceptions to the octet rule, and oxygen, not oxygen, but sulfur here is one of them that can exceed the octet rule. So what we're going to do here now is we're going to take one of these lone pairs on the oxygen and we're going to move it in and show it as a double bond here on the oxygen. When we do that now, a couple things happen. First of all, the sulfur is no longer shown with 4 bonds, it's shown with 5 bonds. So let's go ahead and calculate what the formal charge on the sulfur would be when we have 5 bonds. If it has 5 bonds, we once again go through the formula and we say that sulfur now has how many valence electrons in a free atom?
6.
And in this case here, we're showing how many lone pair electrons?
0.
0 on the sulfur. So it subtracts 0. And the number of bonding electrons now that sulfur is showing is 5, which is half of 10. So again, we have 10 electrons around here. Half of those is 5. So we take 6 minus 0 minus 5, which is going to give us +1. So by putting that extra bond in there, we've now reduced the formal charge in the sulfur from a +2 to a +1. Let's look at what's happened to the oxygen now. The oxygen here has 2 bonds. So again, an oxygen in here with 2 bonds. We can then calculate it like this. We'd say that we're going to take the number of valence electrons in a free oxygen atom, which is how many? 6. Then we're going to subtract from it the lone pair electrons. And how many lone pair electrons are there altogether? Right now we have
2 lone pairs.
2 lone pairs, which is a total of how many electrons? 4. And then we're going to subtract from this 1/2 of the bonding electrons. So right now, the number of bonding electrons is 4, and half of that then would be 2. So we take 6 minus 4 minus 2, which is going to give us 0. And that means that this oxygen up here has a formal charge of 0. And so now we've at least accomplished the goal of having reduced this formal charge down from, well, we've reduced it in the sense that we're looking at the absolute value. We're trying to get those values as close to 0 as possible, and we have one here that's 0. Now this still isn't the best way to write the structure. What is another way we could reduce this even further or make it better? What do you think we could do? Yeah.
Double bond.
Well, maybe not all of them, but maybe one more. Okay? If we put in another one on here, we know that by putting in another one that the formal charge in this oxygen now must become 0. And then if we look at what happens to the sulfur in this case now has how many bonds?
6.
Okay, so now if we have 6 bonds, we want to calculate that formal charge. We calculate by taking the number of valence electrons in the free atom, which is 6. We subtract from it the lone pair electrons, which in this case would be 0. And then now the number of bonding electrons that this sulfur has is 12. Half of 12, of course, is going to be 6. So we have 6 minus 0 minus 6, which is going to give us 0. And so this formal charge here is 0. So you see, if we kept going and double bonding them, if we double bond it again, what's going to happen to the formal charge here in the sulfur?
It's going to get negative.
Then it's going to start going negative, and we don't want it to go negative because by our rules, if we are going to have a formal charge on an atom, that formal charge should be on the one that has the largest electronegativity. And so it still is, and we reduced 3 of these here, 3 of these formal charges down to 0. It's the best we can do. The sum of the formal charges here is still summed to be the charge here on the polyatomic ion. And it turns out that this is probably the best structure we can do if we were to optimize formal charges. So any questions that you have on this particular structure? Okay, couple things. First of all, when we started our work here on Lewis diagrams, we talked about predicting skeleton structures. And one of the statements that was made here was that when we pick out several possible structure formulas, the one in which the atoms have their usual number of covalent bonds is generally preferred. And so one of the reasons why oxygen normally prefers 2 bonds is for a couple reasons. One of them is it starts with 6 valency electrons and it needs 2 more to complete its outer level. But another reason why it likes to form 2 bonds is because it gives us a formal charge of 0. And so there's a couple things then that dictate to us why oxygen likes to double bond. Now sometimes we'd like to find a way to do things without formulas if possible. So there is a way to determine formal charges without a formula. I guess I still kind of use a formula, but we kind of look at it graphically. And what I'm going to do now is I'm going to put this in blue. And we're going to do this based on the definition. And the definition goes back to the bonding electrons here are shared equally. So if the bonding electrons are shared equally, what that means is that if I went here and split these up like this, I'm basically splitting them up, showing that the ones on this side belong to the sulfur, the ones on this side here belong to the oxygen. The one on this side belongs to the sulfur, the one on this side belongs to the oxygen, and so forth. So again, that's simply following the definition of what formal charges are. then if we want to calculate the formal charge, it looks like this. We start with the number of valence electrons on the free atom, which in the case of oxygen would be 6. Right now we're showing 1, 2, 3, 4, 5, 6. So we'd say take 6 minus 6, which is going to give us 0. If we did something like this one, we would say that oxygen starts with 6 valence electrons, and right now we're showing 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is going to give us -1. If we looked on the sulfur, sulfur starts with 6 valence electrons. We'd take 6 minus the 1, 2, 3, 4, 5, 6 on here. 6 minus 6 is 0. And that's the way we can do it then without a formula. We can simply do it graphically and look at how we divide or split these things up. So that is one of the options you can use. Okay, so any questions on that shorter way of doing it? Okay, what's one other thing that this sulfate ion might have based on what we've learned thus far? What else might be present in the case of sulfate? Well, why didn't I put the double bond here? Or why didn't I put the double bonds here and here? Why did I pick these two? What else might exist in the sulfate ion? Okay, I'll give you a minute or two to talk it over, discuss with the neighbor. I expect an answer here when we come back. Talk with the neighbor. What else might be present? Resonance might be. And why might resonance be possible? Right. And it turns out that I didn't know for sure the other day whether sulfate had resonance or not, and one of the students in class looked it up and found out that indeed it does. So it turns out that these probably even aren't double bonds that exist in here. We should then draw out some resonance structures in which we show all of the possible positions that those double bonds might be in. And remember, they aren't even double bonds. It is that there would be some delocalized electrons. These two pairs of electrons would float throughout the structure, and we would then have multiple resonance structures. Okay? So let's go ahead then and look at these next two. And you go ahead and try these out. Let's look at the structures for sulfur trioxide and for the chlorate ion. Sulfur trioxide and chlorate. And for each one of these, for sure start on the sulfur trioxide, and then the chlorate might have a little trick to it. But do with these two what we did here already. We're going to write a Lewis structure that optimizes the formal charge on each atom. So write a Lewis structure that optimizes the formal charge on each atom. check out the sulfur trioxide. See how we are on that one. If you were to just follow the initial rules before learning about formal charge, this is what you'd wind up with. What can we do to optimize the formal charges on this one? Or is this the best structure? Going once. Is this the best?
No.
What makes it better? What would make it better?
You can still double bond the other two.
Okay, if we take this one out, put in a double bond here and here, is this the best? Okay, what's the formal charge on the oxygen in this case?
0.
And how about for the sulfur?
0.
0. Right, we've already calculated this up above. We've shown that when a sulfur has 6 bonds, its formal charge is 0. We've shown that when an oxygen has 2 bonds, its formal charge is 0. So we have a structure here which all of the atoms in the structure have a formal charge of 0. That makes this, as it is written, the best possible structure. Okay, and remember, a quick way to calculate this one would be to go through and simply divide up the bonds if you wanted to do it. We start with 6 valence electrons on a neutral oxygen atom, and we're showing 1, 2, 3, 4, 5, 6 right here. 6 minus 6 is 0. And so we can go through, you could verify that on each one of them here if you needed to. What would make the chlorate better? Of course, we're seeing one trick is to do what with the oxygens? We could double bond them, but how many should we double bond? Should we double bond 1, 2, or 3 of them? Okay, if we double bond 3, let's see what happens. Put in 1, 2, 3 double bonds. If we do this now, let's calculate those formal charges. Remember, the quick way to do it is to do it graphically. We'll split them up. If we split them up like this, we then do our quick way of doing it. We already know that the formal charge on each of these oxygens should be 0. We then look at the chlorine, and the number of, let's see how we do this. The number of electrons on a free chlorine atom is 7. Right now we're showing 1, 2, 3, 4, 5, 6, 7, 8. 7 minus 8 is -1. So we have a formal charge of -1 on the chlorine. Is this the way we want it? Yes or no? And why or why not?
Yes, because it has a negative charge on it.
Okay, we go back to the electronegativities. We check out the electronegativities for oxygen and chlorine. Which one is the more electronegative atom?
Oxygen.
Oxygen is. So do we have the formal charges the way that we should? No, because a negative formal charge, if it exists, should be on which element?
Oxygen.
Oxygen. So what can we do to change this? Take off one of the double bonds, exactly. If we take off one of the double bonds, we can come back here and show that pair of electrons sitting out here. If we have a single bonded oxygen, as we've shown above, a single bonded oxygen is going to have a formal charge of -1. So we'd have a -1 formal charge out here. Now by default, we know that they should sum to be -1 on here, so we could just that way say, well, we can assume that this chlorine is 0, but it's also good to verify it. So if we want to verify this graphically, we go ahead and split these up. We'd say that the chlorine starts with how many valence electrons in a free atom? 7. And right now we're showing 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. Looks like this would be the best structure for the chlorate ion, because this is the one that optimizes the formal charges and is the one that gives us the more negative formal charge assigned to the more electronegative atom, which again is the oxygen. So any questions on this one? And so of course, while it's very tempting to go through and double bond all oxygens like we did here, remember we stopped doing it on the sulfate for the very reason that it starts making sulfur have the negative formal charge. We need to stop doing it on this one as well with the chlorine, because we want to make sure that the negative formal charge stays with the oxygen. And what else would this structure probably have? We probably have resonance, exactly, because we don't know which pairs of atoms to show the double bonds. So in that case, there's probably resonance that exists, and those valence electrons would float throughout the structure. All right, that takes us through everything here in Chapter 9, with the exception of bond energies. And bond energies now is something that you are going to be responsible for only on a qualitative basis, not on a quantitative basis. In other words, I think the last section there in Chapter 9 has you calculate bond energies and like whether reactions are endothermic or exothermic based on the bonds that are formed. You're not going to be responsible for that. However, you will be responsible for it in terms of a qualitative perspective. And in a qualitative perspective, what we should know is this. First of all, you can calculate the enthalpy change for a reaction, if we wanted to, by looking at the energy that goes into breaking bonds and the bonds that energy that goes into or that is released by bonds reforming. And so we said energy goes into breaking bonds, which means that they are endothermic, and energy is released when bonds are reformed, which means it is exothermic. And that should make sense. If you look at something like this, if they're bonded or held together, it takes energy to pull them apart, to break them apart, so that should make sense that it's endothermic. And then the reverse must be true, that if bonds are going to be reformed, that it would give off energy or would be exothermic. Then as the bond order increases, so does the bond energy. So when we look at something like these models right here, I think we talked about bond order in here the other day. What is the bond order for the carbon atoms in these two, for this molecule here? This is the bond order of 1. The bond order in this one here is 2, and the bond order between carbons here is 3. So we simply count the number of bonds between two atoms, and the bond order is equal to the number of bonds between two atoms. We say that as the bond order increases, so does the bonding energy, which should make sense. If we have only one bond holding two atoms together here, that means that should come apart relatively easy compared to something like this, which has a total 3 bonds holding it together. More energy is going to be needed in order to break 3 bonds apart. And then again, we look at the enthalpy of reaction. It's approximately equal to the sum of the bond energies for the atoms broken minus the sum of the bond energies for the bonds that are reformed. What this basically says is this last one. Basically says that if there's more energy that goes into breaking bonds than is given off when bonds are reformed, the process is going to be an endothermic process. And if more energy is released when bonds are reformed than goes into the bonds when they break, then the process is going to be an exothermic process. So if you can describe that or know this stuff from a qualitative perspective, that's all we need to know. We're not going to be quantitative and do these numerically. You might have 1 or 2 mastering chemistry that you will verify it, but we have a lot more. You have plenty of stuff to do on your upcoming exam. You will not be doing this quantitatively on your next exam, nor on the final. So any questions that you have? All right, there's a handout here that I just passed out. And what I'd like for you to do is to go through those. And we only have about 10 minutes left here today. But these are taken from your text. And if you are looking in your text, these would come from numbers 39, 51, 63, and 65. So these are the end of chapter 9. They're numbers 39, 51, 63, and 65. And since we only have about 10 minutes left, you're going to practice. I would practice letter C, B, A, and then of course all of number 65. And if you have the old text, these are numbers 5, 15, 23, and 25.